Today we'll start talking about the famous Dani's correspondence, which is due to Dani's famous paper in 1985. Dani's correspondence establishes the correspondence between the Diophantine approximation problem and the homogeneous dynamics. On one side, you have matrices with certain Diophantine properties. And on the other side, you have trajectories in the space of unimodular lattices with certain topological properties. And Dani's correspondence establishes the relation between those two kinds of properties. Let me start with our first definition. About the singular matrices. An m by n matrix A is called singular if for any epsilon greater than 0 there exists q sub epsilon such that for any capital Q greater or equal to q sub epsilon, there exist integer vectors p in Zm and q in Zn such that if you look at the maximum norm of AQ plus P, here by maximum norm we mean the maximum of all the components of this vector in Rm such that this maximum norm is less than or equal to epsilon times q raised to power negative n over m. And at the same time, the maximum norm of q, which is a norm in Rn, is strictly greater than 0 and less than or equal to q, capital Q. That is the meaning of A being a singular matrix. As an example, let's look at the situation where the matrix A is a number, namely m and n are both equal to 1. What do you think in this situation being singular means? I'll let you think about it for a while. I will tell the answer later. What kind of number do you think will satisfy this property? I believe it is not hard for you to see that any rational number will satisfy this property. But let us still do it rigorously. Let A or B be a rational number with, let's assume the GCD of A and B is equal to 1. Namely, they are coprime. Then, for any epsilon greater than 0, we take Q epsilon to be constantly B. Then, for any Q greater or equal to Q epsilon, which is B, there exists P as negative A, and Q, which is B, such that the norm of A or B times Q minus P, which is in this situation really just the absolute value, is equal to 0, which is strictly less than epsilon. Now this Q is automatically has a norm less than or equal to capital Q, which is just B itself. And this capital Q is bigger or equal to B, which is Q. So any rational number is singular. This is the easy part. Now conversely, do you think that any singular number is also rational? The answer is yes. Any singular number is also rational. However, the proof of this is quite involved. To this end, we need to use the theorem I did in another video, called the Hurewicz theorem. Hurewicz theorem says, for any irrational number alpha, there are infinitely many rational numbers p over q, such that alpha minus p over q's absolute value is bounded by 1 over square root of 5 times q squared. And this square root of 5 is actually optimal. So what do I mean by saying that square root of 5 is optimal? By this we mean for any epsilon less than 1 over square root of 5. This property fails. Namely, the absolute value of alpha minus p over q is no longer less than the epsilon times 1 over q squared for infinite many rational numbers p over q. So, for any irrational number alpha and epsilon less than 1 over square root of 5, there are no longer infinitely many rational numbers p over q satisfying this inequality for epsilon times 1 over q squared. To put it another way, this means all but finitely many p over q's where PQ are coprime, we have the absolute value of alpha minus P over Q is greater or equal to epsilon over Q squared. So now let's multiply both sides by Q. And we get the absolute value of alpha Q minus P is greater or equal to epsilon over Q for all but finite many P over Q with PQ coprime. And that is the meaning of the optimality of square root of 5. So if alpha is not rational, namely irrational, then alpha is not singular. By taking the epsilon less than 1 over square root of 5. Let us still do it more formally. For any epsilon less than 1 over square root of 5, and any q sub epsilon, a real number, there exists a capital Q, which is taken just to be a little q, greater than q epsilon, such that the absolute value of AQ minus P is greater or equal to epsilon over Q, which is epsilon over capital Q. For some P in Z. And this follows from the optimality of square root of 5. So this shows that alpha as an irrational number cannot be singular. So being rational is same as being singular in the dimension 1 case.